Welcome. Today's notes worksheet is entitled Complex Numbers Day 2. This lesson just gives us the opportunity to continue the process of working with complex numbers. So we'll start it out with a little investigation and talk about square roots of negatives, and then get into some quadratics and work with their solution sets a little bit here. So let's start it out. I've got at the top here simplifying square roots of negative numbers. And what we're going to do essentially is use that nice product property that we did before when we worked with square roots and also radicals, if you remember, that family of expressions. So we're going to use the product property and basically start talking about I as a factor. Okay, so use that product property to write I as a factor. And again, up until this point in time, obviously we cannot express this number in the real number system. And we had kind of talked about that issue in the previous lesson. And so now, rather than just saying this is not something that we can represent, we've expanded our representation of numbers beyond the real number system to include the imaginaries. And so now we're going to be able to represent it. And so in this particular case, just using the product property, I would just take this nice and simple and just say that the square root of negative 25 can be written as a product of the square root of 25 times the square root of negative 1. So we pull out that square root of negative 1 as a factor of the square root of negative 25. And now nice and easy here, square root of 25 just happens to be 5. This, of course, if you need to, please look back at the previous lesson, but this was defined very specifically to allow us to do this, and that is just I. That is the imaginary unit. So the square root of negative 25, rather than just saying no value or no solution, which your calculator would do in the real number system, we can do it. Now extend it beyond. Just one note on this. There is no plus or minus in front of this, because I am not undoing a square in an equation. Okay, this is one single number, and I represent it as one single number simplified. So just be very clear on that. No plus or minus on these. You'll see the context for doing this in a little bit. All right, so let's do letter B, just using the product property. Perfect square that goes in 24 happens to be 4, so I would treat this the exact same way as I did before when we looked at radicals, except in this case I'd also include the factor of negative 1 under the radical there. And so when all said and done, square root of 4 happens to be 2, square root of 6 cannot be simplified, and square root of negative 1 is I. And that looks perfectly fine right there. This is just a product of 3 factors, so however you write this, it's fine by me. You see this quite a bit as something like a 2i root 6. You'll see that written quite a bit. They mean the exact same thing, of course. It's up to you how you want to express it. Just be a little careful, if you would. You just have to be careful about that I. This would not be correct. So you can't have the I underneath that root there. It is a factor unto itself, and you have to treat it as such. So this would be wrong right there. All right, very cool. Let's move on to letter C. Would love for you to pause the video, to be honest, and try this one on your own. Just see if you can simplify square root of negative 80. Again, rather than saying can't do it, let's do it. So 16, I think, is your winner on that, by the way. And the only difference, of course, is I include the square root of negative 1. Here's my 4, here's my root 5, and here's my I. And as I said before, not to be too redundant here, but basically, if you want to go ahead and write it as 4i root 5, that's fine by me as well. Either way works. All right, cool. There's a great little investigation here, and just kind of talking about this. This is more number theory than anything else, but I would really like for you to pause the video here and take a look at it, and just answer yes or no. So we basically took this square root property, this product property, for granted, right? This is what I taught you, that the square root of a times b is equal to the square root of a times square root of b. No questions asked. We probably even got a calculator and we saw it in action that it worked. The question is, does it work for all types of numbers? So even though I said it did, and even though we've been using it now really since the beginning of the year, is it flawless? Let's take a look. All right, so I'm hoping you've, at this stage, answered yes or no, so I'm going to run this fairly fast. This is square root of 36, which is 6. This is square root of 4, which is 2, so this is 6 equals 2 times 3. Yeah, of course. So with two positive numbers, and I hope this works because this is exactly what I taught and we've been using it, yeah, this works. Two positive numbers, it works perfectly. Well, the next one, guys, if I look right here, square root of negative 4 times 9, that's square root of negative 36, which happens to be 6i. So the left side is equal to 6i, again, square root of negative 36. And in this right here, if I look at it, this would be 2i times 3. Sorry for the sloppiness there, but I think you can see it. So 2i times 3, which is also 6i. Is the left side equal to the right side? Yes, no doubt. And that's looking good. So one positive, one negative, it seems to work. That product property is nice. As a matter of fact, take a look up here, guys. I pretty much have that in place, so I do hope that works. How about this one? Square root of negative 4 times negative 9, that's 36, and square root of 36 is 6. Then, guys, I've got a 2i times 3i. And what do you think? Here I get 6i squared. Is 6i squared equal to 6? Absolutely not. 6i squared is equal to negative 6, and as a result, that actually doesn't work. So what I've been using, at least the context that I've been using it, yes, they work. But it's just interesting to see numerically, if you go with two negatives, it actually doesn't work. You can't break them apart and put them together like that. So anyway, here's what I'd say. The product property, kind of interesting. Again, number theory, nothing more. I think it's pretty cool. But just trying to elaborate on something that we've been using, and we kind of took it for granted that it always works. But as you can see, it's not the case. So that product property does not work for two negatives. Awesome. All right, let's move on to the next piece. So one of the things we need to kind of come back to is working with the quadratic equations. And rather than getting a solution set that potentially is just no real numbers, let's see if we can represent it appropriately. Okay, well, let's see what we've got going here. We have methods for solving quadratics, so let's utilize them. There's factoring, there's undoing the square, there's completing the square, there's quadratic formula. So let's get into this one right here. I would definitely argue, and I hope you would do the same in its recognition, that this is a perfect candidate for undoing the square. So in this case, the 36 comes over to the other side, and I do get x squared equals negative 36. If we're just solving for the variable, it is time to undo that operation of squaring. Undo the square. Those cancel, of course. Now I get my plus or minus, and again, please recognize that the reason I get a plus or minus here is because we are working in an equation where we're undoing the square. So both roots work in the equation. Now the question, of course, is, what is the square root of negative 36? So as we've potentially seen before, well, if we've gotten this before, we would basically say, oh, there's no answer because there's no number that multiplies to negative 36 times itself. There's no square root of negative 36. But in this case, now that we've expanded our notion of numbers beyond the real number system, we can represent it. And I hope you see it's 6i. All right, so there you go. And by the way, if I made you, and I won't, but if I made you put 6i back in for x, would it work? If I made you put negative 6i back in for x, would it work? Yeah. Great. Let's go get b. So I would look at this. Unfortunately, it doesn't factor. I would look at it again and realize can't undo the square. So let's go with the completing the square. I think that is a great method to solve. Good technique. So x squared plus 2x on that side Let's bring the 2 on over to the other side. Give me a blank if you would. All right, got to get automatic here, kiddos. What's going to be put in here to complete the square? How about a +1? And obviously balance is necessary here. Add the 1. And we've seen this before, of course, but the whole reason for completing the square is because of the way it factors. This works beautifully to just x plus 1 squared. And then on this side, of course, you get -2 plus 1, which is -1. I'm going to undo the square at this point. Again, the whole reason for doing that is to change it in a more user-friendly form. And I've done that right there. Square and square root will cancel. I get x plus 1 equals. Plus or minus, of course, everybody. And what is the square root of -1? That's just I. So you could put it as a 1i if you'd like. Not a big deal. And then how about we subtract the 1 essentially? So let's bring that 1 on over to the other side. Just be a little careful. Over the years, I've seen students forget that when it does move over to the other side, it does change the sign there. And so in terms of a nice imaginary number, of course, it works. -1 plus I is a solution to this equation right up here. -1 minus I is a solution to that equation. Both work. So you can see, obviously, our solution sets are now in the imaginary number system. And rather than just saying, oh, we can't solve, you do see that you get 2 solutions here. Okay, very cool. Let's go get letter C. Now, I know this is not quadratic, but it does have a little bit of a feel to it, and we'll probably see some more of these in action. Because this is potentially the first time seeing this type of equation, I'm going to tell you it factors. And it factors in the exact same way that a quadratic does. The only issue is rather than x and x, in order to multiply to x squared, it must be x squared and x squared in order to multiply to x to the 4th. Otherwise, everything else runs beautifully here. It is factorable, and so 2 numbers that multiply to 4 and add to 5, I'm thinking 4 and 1 would do the trick. And this is the factored form of this right up here. We have seen, of course, a difference of 2 squares. We always talked about the sum of 2 squares being prime, and they are prime in the real number system, but that doesn't mean we can't get something out of it in the imaginary number system. So let's do exactly that. Anytime we have factors set to 0, that is a great position to be in. And so we set our factors to 0, and let's get the variable by itself. Subtract the 4. Undo the square. And I'm hoping you would see in this case, plus or minus, square root of -4 at this stage, 2i. I repeat that process one more time here. X squared equals -1. Undo that square, and because I'm undoing the square, I do take the plus or minus of the root. Square root of -1 represented as I. And there are your 4 solutions. You are more than welcome to grab a calculator. I won't waste our time with it, but if you want, grab a calculator, put any one of those 4 back in for x, perform those operations. Do you get 0? You bet. All right, one more good one right here. Let's see, put all of our algebraic techniques to the test on this one. I will tell you it doesn't factor. Sorry about that. No undoing the square. I like completing the square, even though it's going to be a little ugly, but I know we can handle it. So here we go. First order of business with completing the square is to make sure we get a single x squared out in front. Because it's an equation, obviously we need to know when to do things and when not, but because it's an equation, I can just divide everything by 3. Balance is necessary, and that should work okay with us. So here we go. And how about a 4/3 on that? And then still equals 0. Still the exact same equation, just now will allow us to go ahead and complete the square. So you need to come into the mix here and fill in a blank for me. That's the key. I'll do that work right here. I think that setup is ready to go for you. But the question I would have for you is, what goes in right there, and hence right there as well? Take the moment. See if you can do it. So what I would do, just kind of thinking off to the side, I would do negative 2/3 and divide by 2, or dividing by 2 is the same as multiplying by 1/2, so if it helps you, multiply it by 1/2. But basically, the bottom line is you just have another little 2 down there. So negative 2/3 divided by 2 is really negative 2/6, which happens to be negative 1/3. That's my b over 2, and now I'm going to square it. And when I square negative 1, I get 1. And when I square the 3, I get the 9, and there's your answer. Hope you got that. Balance, we've got it. Now, of course, complete because of the way it factors. So what times itself would give us x squared? X times x. What times itself is going to give us 1 over 9? Well, 1 over 3. And because the outside and inside would have to combine to a negative 2/3 x, if we were to FOIL, that has to be a minus. So it would be minus minus in the two binomials. Great. Now let's see this piece right here. Got to simplify that. It's just combining fractions. No big deal, everyone. I'm thinking about common denominators here, and in this case, common denominator would be 9. And I'm thinking this is negative 12 over 9 plus 1 over 9. So hopefully you're able to put that together quickly and cleanly. I might have to maneuver around a little bit on my board here, but basically you're going to go ahead and undo the square at this stage. I'm going to bring this on up, and I get x minus 1/3. Again, you see the square root of the negative. Rather than saying no go, let's make it happen. So first and foremost, plus or minus. What I would do is just kind of look at it from the top perspective, square root of a negative 11, so to speak. I can't really work with the 11, but I can work with that negative by pulling out I. And I hope that's what you've seen from the beginning of the lesson. I can come out as a factor. Then, just as it happens, square root of 9, everybody, happens to just be 3. So I like playing it just like that. If you want to play around with it a little yourself and get something slightly different, that's fine. But I think this is a pretty clean version of what you would get on the right-hand side. Cool. I think we want to just go ahead and add the 1/3 to both sides. So you're going to get 1/3 plus this. And the beautiful thing about this, of course, is that it is the same denominator. So why not treat it as such and put it all under? There we go. I like that solution set right there. Is it an easy, quick, enjoyable solution set? No, it looks a little comprehensive in nature, but whatever. Hey, it is what it is. If I put those two values, 1 plus I root 11 over 3 back in for x, did all those operations, it works. If I did 1 minus I root 11 over 3, it works. All right, so the nature of the solution sets are changing dramatically beyond the real number system. Hopefully it's working for you. All right, let's take a look at the next piece. So maybe we'll do a little quadratic formula program, get this moving along a little bit. And let's see what we've got. So the top says, what is the quadratic formula? Obviously, we've actually proved the quadratic formula. It took some time. And we got this, of course. Throw that over 2a, and we're in business. Now, that happens to be a particular part of the quadratic formula that has a name, and it has some bearing on working with these types of equations. So we're going to just investigate that piece. So it says the part under the square root in the quadratic formula, which of course is the b squared minus 4ac, is what is called the discriminant. And its value provides information about the character of the solutions of a quadratic equation. Very nice. So the second investigation on this worksheet just deals with that discriminant, the nature of the discriminant, and in what type of answers we're getting when we solve the equation. So we're going to obviously use the technology to expedite this along a little bit. I've got 6. I think what I'll do is at least a couple with you in terms of the calculation. Maybe I can ask you to do a couple in terms of the calculation, and then maybe I will have to fill in my table just with some things I have on my paper. So let's get this going. b squared minus 4ac. I hope everyone's kind of cool with a being the number in front here, b being the number in front of the x value, and c being the constant. So starting this out and just fill in this table, I think we'll go just sort of these two columns first and then we'll deal. Although we'll see. But anyway, let's go ahead and do the discriminant. So this would be negative 4 squared. And be careful when you do these on the calculator. That negative 4 does have to be in parentheses. Minus 4 times 1 times negative 12. Now I will grab the calculator here to kind of do this. I can see what we're going to get, but want to just make sure that we type in things correctly. So what I mean by putting in the negative 4, when you square a negative, it does have to be in parentheses like that. So negative 4 squared, there's my minus 4 times 1 times negative 12. And we get 64, which is great. There we go. So 64 is what we would call the discriminant value for this particular equation right here. Is it positive, is it negative, or is it 0? Of course, it's positive. All right. Well, here's what I'd ask. Literally, just pause the video for one moment. Pick any one of the remaining 5, and make sure you're able to calculate a discriminant. And what I will do is come on back here in just a sec, and I'll just write my numbers in. I have my sheet with me, so I've done this before, and I'll put them in place. Well, the hope is that you've at least done one, maybe more. And the discriminant here is 76, so that's positive. Discriminant here happens to be 0, obviously 0. This one happens to be 0, same deal. And then these two happen to be negative. So negative 3 I got as the discriminant for that one, and negative 36 for the discriminant on this one. All right. So I think we're ready to roll here. Notice how I set it up. Obviously, there's some rationale with these 6, 2 of each. Just one to see what we get and one to confirm it. So based on the nature of our discriminant, we're going to talk about the types of solutions we get when we solve these quadratic equations right here. Now, if I asked you to solve these, you would do any number of things, of course. You would factor, undo square, maybe just on this one, complete the square, whatever the case may be. And you get a particular type of answers, a solution set for each equation. And so let's talk about those. Rather than doing them all algebraically, let's shortchange it a little bit. Let me see if I have the program on here. Yes, I do. Perfect. So get a little practice with this one if you would. Using the program, of course. What I want to know is what type of numbers do we get in our solution set? So what is A? 1. What is B? Negative 4. And what is C? Negative 12. And notice we get 6 and 2. Perfect. Do you see that they're real numbers? And do you see they're distinct? They're different. Okay. So here's what I'm going to write. We get, for right now, I'll shortchange it. When we conclude it, I'll put it in a little more complete way. But we get 2 real solutions. And excuse my shorthand there. Just trying to work with the time a little bit on this one. All right, let's keep going. Again, it would be great for you to do a couple, for me to do a couple, but whatever. Let's go hit our program there. Nice. Let's see, I've got 1, 6, negative 10. Probably not so clean this time around. Do those look like real numbers to you? Absolutely. They happen to be irrational, by the way. The other ones were rational. These happen to be irrational, but they are real and they are different. So same thing, guys. Look at that. A positive discriminant, and we ended up getting 2 real solutions when we solved the quadratic equation. Nice. Let's keep it going. All right, next one. Program's in place. I'm going to roll with this beautifully here. How about 1, and then 8, and then 16. Ah, look what happened here. Are they real numbers? Yes. But what do you notice, of course? Yeah, they're the same. So we get, basically, you get 2 answers. Remember, every quadratic has 2 answers to it. In this case, it just so happens the 2 answers are the same number. So we're going to call it one repeated real solution. And by the way, what do we mean by repeated? If I asked you to solve this, just FYI, you would factor it. And you would say x plus 4, right? And so you obviously see that -4 comes from two different factors. And we'll explore that idea quite a bit this semester. All right, very cool. Let's go on to the next. I'm rolling nicely. Maybe you filled in a couple things already. If you have, you can keep going with this. But I have to do it up here in real time. And same deal. Look at that. Discriminant was 0, and we got the same scenario. We got a real number. It just so happens we get it twice. So one repeated real solution. Awesome. Now what happens here? Negative discriminant. Let's see what we end up getting. So I'm going to hit my program again, go quadratic formula. Looks like 1, 1, and 1, huh? Here we go, 1, 1, and 1. And look at what we get here. In this case, is there any real number in existence that would make this equation true? Absolutely not. So there are no real solutions. What types of solutions are they? They're imaginary. I could change the mode on the calculator and kind of get those imaginary systems. I'm going to avoid doing that for right now. That's not what I'm interested in at this point, but that would be the case. Oops, this should be 2 imaginary solutions, because remember, every quadratic does have 2 solutions, and we do need to acknowledge that. So let's put that into the mix. So 2 imaginary solutions. Oops, did it again. There we go. Better. All right, 1 to confirm, and then let's conclude this thing and do a couple examples to wrap it up. So quit that. Program one more time. I'm persevering right on through. And here's what I have. A is 1, B is 0, C is -9. Oh, I'm sorry, +9 there. And same deal. All right, so as a result, you don't get a real solution. Tried to do it on the calculator there, wouldn't give it to us. Again, if I went imaginary mode, and if you want to view that with me, you're more than welcome to. Just call me over. We could take a look at that. But you'd get your 2 imaginary solutions. Okay. So conclusion, as you can see, everything was kind of laid out, I think, pretty coherently in this table. But let's go ahead and put the conclusion together. So the discriminant, again, as you can see, tells us kind of the nature of the solutions that we would expect. We'll revisit the quadratic formula in just a sec to get a little closure on it, but let's put this in place. So if the discriminant is positive, that means greater than 0, you get 2 distinct real solutions. Absolutely. If the discriminant is 0, you get 1 repeated real solution. So you get basically the same number coming from 2 of the same factor. So 1 repeated real solution. And if the discriminant is negative, then of course we get no real solutions. We get 2 imaginary solutions. Maybe pure imaginary numbers, but not necessarily. So 2 imaginary solutions. Basically, complex numbers that are not real. Awesome. And why, of course, is that? If you look at the quadratic formula, you can see sort of what should happen here. Remember that discriminant is underneath a square root. So if that discriminant is negative, can I take the square root of a negative in the real number system? No. And so as a result, no real solutions. We start talking imaginary. So I hope that makes sense. Look at the quadratic formula, look at the discriminant, and you should see that these 3 conclusions really make some decent sense. Hey, let's round it out on just the last couple examples. So example 3, complex numbers, not when b is 0, but when b is not 0. So complex numbers that are solutions to a quadratic equation always appear as, I threw in the as. let's see, look at your solution sets for these equations right here, 6i and negative 6i. What's their relationship? Negative 1 plus I, negative 1 minus I. What's their relationship? Look at this one, 1 plus I root 11 over 3 and 1 minus I root of 11 over 3. So those solutions always appear as, coming right from yesterday's lesson, conjugates. Always as conjugates. And that's what you're going to see. Cool. And we'll expand on that notion quite a bit later on this year. But that works out really nicely. I hope you saw that already. All right, let's do example 4. So an object is being projected vertically upward. Its height after t seconds can be modeled with this function right here. I'll box that up. So a little projectile motion. Will the object reach a height of 100 feet? Why or why not? Now, I'm going to go about this in what you might consider a roundabout way. It's just to emphasize this piece. I know that we can use the technology to shortcut this quite a bit, so bear with me on it though. Will it reach 100 feet? So basically it's asking, if this is 100, is there a time that it will hit it? Is there a value for t that will make this equation true? Well, I'm hoping everyone would be in agreement that basically we'd bring this on over to get it in standard form. So 4 minus the 100 looks just like that right there. And I know, I know we can go ahead and use our program just like I did above and find out if there is a real number for t that makes this equation true. Obviously, guys, if there's a real number for t, then yeah, then there's a time where it hits 100. If there are no real numbers for t that satisfy this equation and only imaginary numbers, then obviously it would not hit 100. Is everyone okay with that explanation? So again, I know we can use the graphing calculator in the program to pull it off. What I want to do is just focus on the idea or the concept of the discriminant. So here's what I'm thinking. Everyone just write the word discriminant because this is how I'm going to focus in on it. And that discriminant, of course, is b squared minus 4ac. So I would ask you to do this. I have it on my paper, so I'm going to shortchange this just a touch. I'm going to ask you to do the calculation and make your own conclusion for a moment. So there, everybody, is the discriminant. And if you calculate the discriminant, and please do at this point, what do you end up getting? And so as a result, when I calculated the discriminant, I ended up getting negative 2048. So now you tell me, will the object reach a height of 100 feet? No. Because if the discriminant is negative, there are no real numbers for the variable that satisfy this equation. And so again, nope, absolutely not. And I'll just write it as there are no real number solutions for t. So in terms of this application right here, in the real number system, nothing works. In the imaginary system it would, but that's irrelevant for our purposes here. So no, there are no real number solutions for t. And we've got it. All right. Cool. I like that. Just a last emphasis on that discriminant, kind of seeing that in action. We'll work with the complex numbers a little bit, kind of that second piece, and let me know if there's anything I can clean up for you in terms of explanations or help you with any problems at all. Thanks a lot for listening.